Please welcome founder and CEO of Dyndrite, Harshil Goel.
Thank you all, and welcome to DDC 2021. It's my pleasure to have all the attendees, the speakers, and DDC members attending today. A number of people ask, why do we even throw this conference? The idea of this conference was to not just highlight, of course, what we're doing over the next year, but to highlight the aspirations, the challenges, and the new technology that every single DDC member is bringing forth. The idea was to work collaboratively and figure out ways to solve real problems and real challenges for all of our collective customers. As you can see, we have an awesome lineup today, ranging from machine manufacturer CEOs like Sam O'Leary and Blake Typel, all the way to computer and hardware manufacturers like Sean Young from NVIDIA and Brent from Ansys as a software vendor. The idea is to bring together machines, software, and materials all together to make something kind of awesome happen. So the existing DDC members has been steadily growing over the last, I'd say, about 12 to 18 months. We've been slowly, steadily adding new types of folks from software and hardware to even new types of machines and processes. So with that, I'd like to formally welcome our latest two members, Czar and Ascension. I believe these are two key and pivotal members because everything about why they're joining has to deal with production. Production for binder jetting and improving processes, enabling newer and more sophisticated toolpaths, production in an HSC environment, allowing you to print much, much, much faster. And at the end of the day, if additive is going to grow and evolve, as Greg Moore said earlier, we have to go to production and we have to codify our practices. So what is Dyndrite and what's our mission? As you saw in the video, our goal is to fundamentally change how geometry is created, transformed, and transmitted on a computer. And the idea here is that the existing software just simply is a bottleneck to most of the processes that we have. You'll see it as a recurring theme in not only my talk, but a variety of talks. And the idea here is, can we get software that dramatically changes the performance of additive so that additive manufacturing can actually level up, to provide, the ability to solve for a new ocean of possibilities and to push the boundaries that, we're all, I think, struggling with from a productivity and scalability standpoint. We've had kind of an awesome year. I'm not going to refer to the elephant in the room, but, a lot of things have happened over the course of the year, right? We, for example, have been signing multiple long-term contracts to slowly become an industry standard and leader. HP announced its entrance into software via the HP Universal Build Manager powered by Dyndrite. I encourage you to check out their website via their direct link or our website and get on the beta list. NVIDIA has been steadily pumping out GPU after GPU and new chip after chip, steadily improving literally what it seems like every 6 to 12 months. So in other words, if we at Dyndrite didn't even do anything, the software is getting 2 to 3 to 4 times faster every 1 to 2 years. And then of course, we threw 2 investor days. In light of the current events and situations, right? It was our idea to figure out a way to give back to the industry by pooling together our network to honestly help fund and help all the startups in the space. So between everything that's been going on, I mean, it's been kind of an awesome year, and I'm really looking forward to what's about to happen next. So the crux of my talk is going to be actually focused on raster-based processes. Basically, as everyone knows, binder jetting and raster-based processes like DLP, SLA have been on the rise. And the idea here is manufacturing needs to be enabled by software and compute. So what does that really mean? It means that we're at a unique point in time where the manufacturing hardware has actually surpassed the software. We have machines that can print at a higher resolution than most software can even make. We have machines that can print faster than you can do build prep. And we have machines that can print all kinds of parts that no piece of software can even necessarily even design. And this all stems from 3 key concepts. So on the raster side, we have one key kind of industry standard, 1-bit monochrome, 2D polygonalized rasterized images, right? If all the data that's going to these high-powered machines, which are capable of significantly more, are limited to 1 bit, right? We're losing control, right? And the idea here and the simple solution would be to just simply add color and grayscale to go much beyond where we're going. The second issue that is a recurring theme is compensation. Regardless of whether you're dealing with a powder bed fusion process or a sintering process, which requires a green part, compensation is the name of the game. Hours and days are spent simulating it, and materials are qualified to go handle this. This basically reduces the freedom of parts that we can use and the freedom of the materials that we can use, and clearly the answer needs to be a generalized anisotropic compensation API. And finally, we're back to the ever-increasing march to how all machines are getting bigger, faster, more resolution, and the people who are using them are generating more and more complex parts. In short, the answer here is power. And to summarize it, the answer here is to use the engine that we've been developing to give back power, freedom, and control in all of these processes. I'm thrilled to announce the set of raster processes and announcements and APIs that we've developed. I believe that they're going to dramatically push the limits of what's already possible. They're certainly pushing them with already a number of key partners. You can imagine what we're probably trying to do with Czar to simply push the limits of what a printhead could even do. So let's dive in a little bit deeper into one of these topics, grayscale. So the idea here is when we have parts, we want to segment them and we want to apply advanced toolpathing. In a raster setting, advanced toolpathing can mean all sorts of things like dithering, anti-aliasing, etc. We're today going to be focusing on grayscale and beyond. The idea is to take a part and divide it up into all of its key segments, whether it be the core, the shell, whether it has a lattice structure, the outside, the inside, specific areas near the shell. The idea is that we can embed metadata into all these processes. But to what end? So what you're seeing here is a high DPI image that has come out of the engine. And the idea is to take this data and dramatically improve the printing process, whether we're enabling functionally graded materials, whether we're creating an efficient way of generating challenging bid files, or handling metallic components and exposing different ways to make improved coils, heat exchangers, nuclear reactors, etc. The idea here is we can use this grayscale to fundamentally solve major physical and material graded problems. With this extra dimension that is now available in the toolpaths, the types of parts that people can make have significantly improved. Moreover, we suspect that a number of people will use this to improve the part quality and finish, because now you can have a graded grayscale on the edges. The next key thing that we'd like to talk about is anisotropic compensation. Right? It's clear that in order for mainstream adoption, we need tighter tolerances, and this needs to happen much faster. Right? We can't spend 10 to 15 hours compensating something just so we can print it and hope to God that the green part that comes out will come out the right way. And so to address this key fundamental issue, we decided that it made sense to create a number of geometric APIs for generalized anisotropic compensation. The idea being that if already right now, if you give the engine 6 scalar values, 3 for scaling in X, Y, and Z, and 3 for offsetting or compensating in X, Y, and Z, you're now able to fundamentally attack some of these hard and difficult problems quicker, better, and faster. You're using the GPU to fully modify all of these images. And what does this mean? It means more materials, more part families, more printer companies and ISVs generating IP, and quite honestly, faster and quicker qualification. The idea here is we're trying to build the tools to fundamentally accelerate how quickly people can develop sophisticated strategies. It's our goal to essentially be the best mathematicians in the room and enable every single one of our partners to generate more and more IP to run their machines to the limit. So let's dig again a little bit deeper. So here we have a test geometry. It's basically a helical fluid channel. The idea was it has a bunch of thin walls and it includes positive and negative features that will receive corrections on the order of the feature sizes. Of course, showing anisotropic compensation is difficult because we're talking about microns, not meters. And the idea here is we're specifically trying to show in this example how this anisotropic offsetting is being used in this raster process to calibrate the machine. So in this world, and you might have to squint a bit, you'll see that we have a number of slices, and you can see that there's a certain level of black, white, and gray in these existing slices. We've now conducted an anisotropic offset on these slices, 40 microns in X, 40 or 60 in Y, and 80 in Z. And now you can see two key fundamental differences. Number one, because we are doing an erosion, you're going to see more white on the right, right? So you're seeing those rings and those little blemishes kind of contract a bit. You're also going to see the fact that the angle of the darkness in the ring is also changing. This is because we are offsetting in Z as well, and because it's a helix, we're just traversing further and further up the helix. Again, the idea here is not that we have invented the best way to go and compensate parts. The idea here is we've been developing a generalized API so that more and more people can take a much more sophisticated approach to doing this. The next thing I'd like to touch upon is performance. And if I could be given the screen share, that would be helpful. Can folks see my screen? Someone should give me a thumbs up from our team.
Yes.
All right. So what we have on the screen right here is a bunch of heat sinks, right? I have no idea how well this is coming across in the Zoom from a frame rate standpoint, but we are at 30 to 60 frames per second, right? And this is kind of a funny looking part. And the idea here is we're going to just simply take this part and we're going to go slice it at 50 microns. Okay, and of course I will shut off the visualization so I can give the GPU as much memory as humanly possible. So let's hit apply. What you'll start to see here on the right is the GPU spinning up. You can see the CUDA cores are running at max capacity. And you're seeing this oscillatory motion, and basically the slice is coming in on powers of 2 over and over and over again. Right? You can see how fast this is happening. You can see specifically the oscillations between when something is being computed and when it's being transferred off the disk. Right? This will actually be merged enough so that it'll be even faster. But the idea is we're generating high resolution images for this heatsink, on the fly live during the Zoom meeting, and we're already done. Right? And this is simply because the GPU has dramatically parallelized this process. So I'll stop sharing my screen and go back to the slides. So why is this performance important? Well, a number of things, right? We're not doing performance for the sake of performance. We're doing performance for the sake of what it will engender and enable from a business process standpoint. Being able to slice significantly faster allows us to A, try and test and simulate quicker, allows us to hopefully B, keep up with the machine, and C, the performance is necessary because one of the key values of 3D printing is the fact that complexity is free. But we all know that that's actually a lie. Complexity is not free. It's limited by your compute and your software. And so how can we, Dyndrite, figure out new and clever ways to use the existing software and hardware and the new, for example, NVIDIA GPUs coming out to push the limits of what's possible? Can we truly flip the paradigm of the manufacturing hardware being, much better than the software? So let's see if we can advance the slide again. So we've been talking quite a bit about raster processes, and I'm sure there are a number of people in the room wondering what else, what else could we possibly be doing? There is actually one more thing that I'm actually pretty excited to announce. It's the concept of support-free printing that I think everyone has been seeing all over LinkedIn and social media and on the internet. The idea being that it's all about the toolpaths and what's kind of important here. So I don't need to go through why support-free printing is important in a laser powder bed fusion process, but I think I can joke ironically about the key pillars of support-free printing. So the first pillar is a geometric query, right? Dyndrite is going to be providing APIs to enable sophisticated geometric queries. A number of folks are already familiar with upskin, downskin, and inskin, right? And applying specific parameters to those specific areas in a slice. But the idea is we want to offer a much, much broader set of geometric queries to enable something very clever. The clever stuff is more and more advanced toolpaths and more recipes and IP. The idea here is, can we figure out a way to enable every machine vendor on the planet and every single customer end user on the planet to quickly iterate in an automated way to generate new toolpathing strategies, new geometric queries, and then codify that into IP and recipes that they can either sell, keep to themselves, or donate to the public domain. The idea here is we're developing IPs to enable this IP generation and development, and again, to provide the fastest mathematics engine on the planet. So what does this look like? So we just talked about geometric queries and segmentation, right? And basically the simplest way to show that is what one of our applications engineers, Dalen, cooked up. You're seeing here essentially a sample part. It has an outer ring, which is thick. It has an inner interface, and then it has a number of fins. As you can see, zoomed in, we've applied a number of different hatching and toolpathing parameters to each of these sections, right? And these were all done via a specific type of geometric query. So the idea here is we want to enable people to make lots and lots of recipes and enable faster parts and newer types of parts quickly. The other type of query that we're enabling is a distance-based one. As you can all tell, we have a pretty darn fast voxel system internally. And the idea is that if you wanted to detect fins or near surface features, you'd simply use actually our raster processes in our voxel engine to also enable these very fast and very sophisticated queries. So let's go generate zones with the distance field. So in summary, we're enabling Grayscale to enable much more sophisticated toolpaths and raster-based processes for binder jetting, DLP, SLA, et cetera. We are enabling a broad-based general anisotropic compensation API to, again, help all the ISVs and printer companies in the space. We are, of course, upping the ante in performance yet again. I think I was seeing a number of benchmarks recently that showed another 1 to 3x improvement. And then finally, we want to do something similar in the vector space, and the first area that we're targeting are toolpaths to enable support-free printing. The idea here is to unlock the capacity of the machines, new materials, and new part families with speed. As mentioned, Dyndrite's mission is to fundamentally change how geometry is created, transformed, and transmitted on a computer. We've seen what's happened over the last 30 years, and I strongly suspect the next year and the next 30 years are going to dramatically change where additive, is going to go. It's going to go from a prototyping process to a production process. It's going to enable a metric ton of IP to be generated. And it's going to fundamentally change the way we decide to manufacture things and how supply chains operate on our planet. I want to take this opportunity to thank all the attendees, developers, and DDC members. I also want to take this opportunity to give a special thanks to all the folks at Dyndrite that made this happen. I genuinely think that you're going to have an awesome time over the next 2 days. Welcome to DDC 21. Enjoy the show.